Let's suppose we're studying hybridization and we can only remember one thing. What's the most important thing to remember about hybridization going forward in organic chemistry? And that's really not the shapes of the atomic orbitals and the molecular orbitals, so much as the geometries about atoms in organic molecules. So in this video, we'll take a few typical organic molecules and we'll just look at what hybridization state the atoms are in. And of course, if they're sp, it's linear, sp2, flat trigonal, and sp3, tetrahedral. So we know that atom will be linear, flat trigonal, or tetrahedral. Let's try a few. Let's look first at the methyl groups of propane. Propane has two methyl groups. They're both the same. They're both equivalent. Both have 3 hydrogens and a carbon connected to the central carbon. That's 4 groups. There's no lone pairs. So the geometry about them will be tetrahedral because the hybridization state is sp3. On the central carbon, the methylene, well, there's 2 hydrogens and 2 carbons attached to that. 4 groups, no lone pairs. 4 groups corresponds to sp3 hybridization, tetrahedral geometry. Let's say we put a methyl group on the central carbon. We could call it 2-methylpropane. Actually, you can save a little bit of energy and just say methylpropane, same thing. Okay, all 3 methyl groups now are the same. They're methyl groups, they've got 1 carbon, 3 hydrogens attached, sp3 hybridized. They'll each be tetrahedral in geometry. What about this central unique carbon? That's a CH, the methine. That's got 1 hydrogen, 3 methyl groups or 3 carbons attached to it, 4 groups surrounding it, no lone pairs. It's also sp3 tetrahedral geometry. Hey, we're on a roll. Let's put 2 methyl groups on the central carbon. We could call that 2,2-dimethylpropane, but really it's the same as dimethylpropane. Put the methyl groups anywhere else and it wouldn't be a propane anymore. Okay, let's look at the methyl groups. All 4 equivalent, sp3 hybridized, tetrahedral. What about the central carbon? That's quaternary carbon. It's got 4 carbons attached to it, no lone pairs. So 4 things, sp3 hybridized, tetrahedral geometry. Okay, let's slip in a double bond here. Propene. The CH3 is sp3 hybridized, tetrahedral. We've gone over that type of thing. But what about the central carbon? Well, it has 4 bonds to it, but let's not get confused about bonds. Bonds don't matter, groups matter. What groups are attached to that central carbon? Well, there's a carbon for the CH3, there's a carbon for the CH2 in the double bond, and there's a hydrogen. Only 3 groups. No lone pairs, because we share in the double bond. So that's trigonal flat. What about propyne? Well, both the carbons in the triple bond are linear because they both got 2 groups attached. The central one has a carbon for the CH3 and another carbon for the CH of the triple bond. And the terminal carbon has a hydrogen and the other C of the triple bond. 2 groups each, sp hybridized, linear. Don't draw acetylenes bent. They're in a straight line. Okay, let's go a little bit more complex. What about 2-propanol? Now we've got a heteroatom to throw in there. The 2 methyl groups are easy, sp3, tetrahedral. The central carbon, a methine, connected to an oxygen, 2 methyl groups, and a hydrogen, 4 groups, no lone pairs, sp3 tetrahedral. But what about the oxygen? Don't forget, the oxygen has 6 electrons to share totally. It shares 1 in the bond to the hydrogen, the OH, 1 in the bond to the carbon, and it's got 4 left. 4 left is 2 lone pairs. So 2 attachments, hydrogen and carbon, two lone pairs, tetrahedral, it's going to be sp3 hybridized. How about propanone? That's got two methyl groups, both the same, sp3 tetrahedral. The central carbon is surrounded by an oxygen and two methyl groups, only three, no lone pairs because it's sharing in the double bond. So that's trigonal flat sp2. And what about the oxygen? Well, it's got two electrons shared in the double bond. It's got four remaining, because remember, oxygen has six total. So that's two lone pairs and a carbon, three groups surrounding it. That's sp2 hybridized trigonal flat. Let's go on to a more interesting molecule. How about this one here? Well, the O in the acid is just like the OH group in propan-2-ol. It's got two atoms connected to it and two lone pairs, sp3 hybridized tetrahedral geometry. The central atom of the carbonyl, three things around it, no lone pairs, sp2, flat trigonal. The oxygen, two lone pairs, the carbon, three things around it, flat trigonal. All the CH2s, tetrahedral, sp3. What about the nitrogen? That's an interesting one. Two bonds to hydrogen, one bond to carbon. But remember, nitrogen has 5 electrons, so there's 2 electrons left, one lone pair. That's 4 things surrounding the nitrogen, sp3 hybridized tetrahedral. And that molecule is a really interesting neurotransmitter, GABA. Okay, let's go on to another neurotransmitter. How about this one here? This is acetylcholine. Okay, CH3 groups, sp3 hybridized tetrahedral, fine. And the carbonyl. The carbon is sp2 flat trigonal, 3 groups around it. And the oxygen is sp2 hybridized flat trigonal, 3 groups around it, a carbon and 2 lone pairs. The oxygen on the other side of the carbonyl group, 2 things attached to it, 2 lone pairs, sp3 hybridized tetrahedral. All the CH2s, sp3 hybridized tetrahedral. But the nitrogen, what about that? Okay, well, it's got 4 things around it, and it shared in the single bonds 3 electrons, and then it donated 2 electrons to bond to the last thing, the last methyl group. So it's got 4 things around it, no lone pairs left. In fact, it's got a positive charge, so it really only had 4 electrons around it, and that's sp3 hybridized tetrahedral. What about this imine here? Simple imine, C double bond N. 2 methyl groups, sp3 hybridized tetrahedral geometry. The central carbon, nitrogen, 2 methyl groups, no lone pairs, because it's sharing in a double bond, trigonal flat sp2. The nitrogen shares 1 electron with the hydrogen, it shares 2 electrons with the central carbon, it has 2 electrons left over in lone pair, it too is flat trigonal. Ethanonitrile has a CH3 group, tetrahedral. Central carbon, it has 2 groups around it, the nitrogen and the CH3 group. It's sharing 3 electrons in the triple bond, 1 in the single bond, no lone pairs, it's linear sp. What about the nitrogen? It shares 3 electrons to the central carbon, it's got 5 totally, so it's got 1 lone pair, 2 groups around it, linear sp. Very quickly, you can get very good at this. And so if I draw you propane and say, let's represent that in the most simple way, actually you can do it with 2 lines where each apex in the shape corresponds to 1 carbon. And you might think, oh my god, he's not showing me the number of hydrogens. But you can work it out because you know the tetrahedral geometry of each carbon because there are no double bonds in that molecule. That's a subtle point, we'll come back to that, but that's the most economical, most beautiful way to draw structures, and I'd like you to understand that as early as you possibly could in sophomore organic. So in summary, it's very simple. The hybridization state of an atom in a molecule is determined, first of all, by the number of groups around it, plus the number of lone pairs. If that corresponds to 2, it's sp linear. If it corresponds to 3, it's sp2, trigonal flat. And if it corresponds to 4, it's sp3, tetrahedral. That's all there is to it. Thank you. I'd like to thank the Fulbright Foundation and the School of Pharmacy at the University of Malaya. These videos will be collected into an electronic book, shortly to be published on iBooks for the Mac, on Amazon Kindle, and it will summarize everything about hybridization and bonding that I've talked about so far in recent videos.